Physical properties. This is going to be a little rough. Physical state, the smaller amines are going to be gases at room temperature. Most of the others are liquids. And so, personally, I find these little tables that they're giving us to be marginally useful. Like, I just don't, this doesn't seem to be that helpful. But C1 and C2, unbranched, primary amines are gases, and the higher carbon ones are liquids. Amines tend to be smelly, which, when you think about them as being ammonia, substituted ammonias, ammonia is pretty stinky, isn't it? It's a very sharp smell, not pleasant in high concentrations. So the methylamines and the ethylamines have an ammonia-like smell. These are the smaller ones. Most of the other amines, the liquid ones, also have strong odors, and those odors resemble that of raw fish. If you've ever smelled decaying fish or rotting flesh, it's not a good smell, is it? There are two diamines that are present in decaying flesh, and they're named putrescine and cadaverine. So these obviously are common special names, but putrid and cadaver, smell of dead bodies. That's fabulous. These are produced when bacteria decompose proteins. There's a lot of nitrogen in proteins, and so when the protein decomposes, it forms a lot of these diamines that have very strong smells. Boiling points. This table's comparing the primary amines with the primary alcohols, and we see that the primary amines have lower boiling points than the alcohols do. So that tells us that the intermolecular forces are weaker in the amines than they are in the alcohols. Now, amines can do hydrogen bonding, but the hydrogen bonding between hydrogen and nitrogen is weaker than between hydrogen and oxygen. I keep hitting the wrong, touching that with my finger. Oxygen is more electronegative than nitrogen is. And so the attraction between hydrogen and oxygen in a hydrogen bond is greater than between hydrogen and nitrogen. As you branch the amine, or increase the, as you go from primary to secondary to tertiary amines, the boiling points are going to drop. Because the tertiary means that nitrogen is not bonded to a hydrogen atom, and so there is no hydrogen bonding. And as we've seen before, as the number of carbon atoms increases, the boiling point goes up. And that's because the larger the molecule, the stronger the dispersion forces are. Solubility in water. Amines are quite soluble in water. Less than 6 carbons, those are infinitely soluble in water. And that has to do with the hydrogen bonding. They've got the nitrogen, which even in a tertiary amine, the tertiary amines cannot hydrogen bond with other tertiary amines. Let's just draw a little picture here. That's an R, and that's an R. So here we've got this tertiary amine. It can't hydrogen bond with another tertiary amine because there's no nitrogen-hydrogen bond. And so that's why their boiling points are low. But if you put water over here, that was supposed to be the eraser. If you put water over here, we can get hydrogen bonding between that nitrogen and the hydrogen. And so the hydrogen of the water molecule will be attracted to the nitrogen of the amine. And so you do have water solubility even in the tertiary amines.